Hello, welcome to this video. So in this video we're going to have a look at how you can tell if you're living on a curved surface, like a curved globe, like the Earth, you can tell if the Earth is curved or not. And this is very important to our study of kind of general relativity, because in general relativity we're talking about the curvature of space-time, but we are living in the curved space-time. So working out how you can tell if a surface or a manifold is curved, if you're living on the curved manifold, is very important. And we'll be kicking off that in this video by looking at two very important bits of maths that we're going to use to help us discuss curvature and general relativity. And these are the Christoffel symbols, or as I'll first introduce on my abstract version of them, connection coefficients, and we'll also talk about the connection associated with these coefficients. That connection is something called the covariant derivative. Don't worry, Christoffel symbols, connections, covariant derivatives, they don't mean anything yet. Hopefully by the end of this video they'll mean probably a lot more. But thank you very much for joining me on this video, and let's get cracking with exploring curvature on a manifold and relating that to our good old friend general relativity and curved space-time. So we're going to start off this video by talking about one way you can deduce curvature, and that is to look at how a vector changes across a manifold as you move it across the manifold, but keep it the same orientation relative to the surface. So to give a visual example of this, I've got this image which is probably one of the best pieces of artwork I will do for this channel, principally because it's got colouring, which is a bit of a step up from my usual rectangles. But in this diagram we can see that there's a person with a ladder on top of their head, and that's saying that they're incredibly physically fit and they kind of want to go all the way around the Earth. And say for example, they might need to escape at any moment, so always have a ladder with them, and the ladder remains stationary on their head as they go around the Earth, so from A to B. Now for them, it will look like the direction of the ladder isn't changing, and if the Earth has a large enough circumference, so if the kind of curvature of the Earth around a small region is fairly small, then to them, as they go around the Earth, they will feel like they're moving on a straight line, and so they wouldn't think that the direction of the ladder, so our vector, if you like, parallel to the manifold, isn't changing at all. However, if we're looking at this kind of ladder, this vector from the outside, it does seem to change direction. So the ladder remains, parallel with itself, according to somebody moving on the curved manifold. However, because the manifold is curved, for our perspective, we can see that, well, the direction of our vector or the ladder does seem to have changed. And that's one way where curvature is different from flat space. So like in curved space, if you move a vector across the surface, if the vector is going to remain parallel with the surface, so remain on a tangent plane with the surface, then the direction of the vector has to change due to the surface being curved. And that means we can transport a vector and keep it as parallel to itself as possible, so keep it unchanged relative to somebody moving with the vector on the manifold. But yet, if the manifold is curved, we can even, for example, consider a closed loop, where if we bring our vector back to where it began, the vector isn't aligned with its original direction. And that's something we're going to look at more in an oncoming video, where we talk about calculating how a vector might change as we keep it parallel to itself as possible whilst moving it on a curved manifold. But it's a good place to get us started for this video, this kind of visual illustration. And what we need to do now is consider how the changing direction of the manifold, so how, if we have a tangent plane to the manifold and we move that tangent plane across the manifold, how the basis vectors on our tangent plane will change as our tangent plane moves across the manifold. Or equivalently, how the basis vectors describing the direction of our ladder will change as we move the ladder across our manifold. Because when we have curvature, the basis vectors will necessarily change. So the thing that is actually describing the change of a basis vector, we can write that as the partial derivative of a basis vector along a particular direction, and when we do that, we'll introduce a symbol called a connection coefficient. So that's where we're going for this part of the video. So remember that for a curved manifold, the basis vectors necessarily have to change across the manifold. And that's because the basis vectors are describing the direction of a tangent plane on the manifold, but the direction the tangent plane will lie on will change if the manifold is curved, if we move the plane from one point to another. So when we have curvature, we necessarily have changing basis vectors. Now, in black space, we can still have a coordinate system like you do in plane polar coordinates, where the basis vectors change. However, when we're dealing with curved manifolds, that's a necessity. It's not, optional. Whatever coordinate system we pick for describing a manifold with curvature, the basis vectors of that coordinate system will necessarily change, which usually means we have to describe the manifold in terms of lots of different coordinate systems connected together. Definitely if you're using Cartesian coordinates, that is what you would have to do. Now, if we want to look at how the change in the basis vectors relates to the change in the vector overall, we can use the product rule, or if you like to be more technical, the Leibniz rule, and we end up with this expression. Now, I'm going to go over this briefly because I've mentioned all of these symbols before in previous videos, but xi means the partial derivative along the ith spatial axis. V with an arrow over it is our vector, and our vector has components Vj, and Vj is the component of our vector in the direction Ej. So, in the direction that our basis vector along the jth spatial axis is pointing. Now, I've gone over that quickly because we've looked at vectors, and how that relates to components and basis vectors on our last video. But as we said, for curvature, the key thing we're really interested in is how the tangent plane to the manifold changes direction, or equivalently how the basis vectors of that tangent plane change direction. So curvature we would expect to be encapsulated in the rate of change of a basis vector along a particular spatial axis. Now, it tends to be the case that we define coordinate systems where a basis vector, where the change of a basis vector along a spatial axis is given in terms of a linear sum of, the basis vectors on that tangent plane. So because of that, using Einstein's summation convention, we can write the partial derivative of a basis vector along a spatial axis as being equal to, the sum over k of our Christoffel symbol, which is that symbol with one upstairs indice and two downstairs indice. It'd be a product of our Christoffel symbol. So the symbol with one upstairs indice and two downstairs indice with the basis vector. And we're summing over all values of k, so we're including, potentially combinations of all our basis vectors, although often the change of one basis vector is just equal to something times another basis vector. But to keep it general, we're using Einstein's summation convention, so we're allowing for the possibility that there might be a linear sum of basis vectors involved. So we're repeating over k, so we need 1k upstairs in our Christoffel symbol, in our connection coefficient, and 1k downstairs in our basis vector. Now, this object with three indices, sometimes I'll call it a Christoffel symbol, sometimes a connection coefficient. Really strictly here, it's a connection coefficient. The reason it's a connection coefficient is because we're not adding any details to it, particularly we're not yet uniquely relating the connection coefficient to the components of a metric. So in this more abstract form, in this more pure form, this symbol with three indices is a connection coefficient. And a very special case of that connection coefficient is a Christoffel symbol, which we'll come on to at the end of the video. We'll have an equation for calculating the Christoffel symbol from the components of the metric. So, we've introduced the connection coefficient, and we said it's related to curvature, so how our basis vectors change. But what we haven't done is actually given some kind of notion of a gradient that can describe how our vector is changing. That is, we haven't introduced something that is called the connection. And as you might guess, the connection, also known as the covariant derivative, is related to the connection coefficients. But the connection essentially describes how a vector changes as we move it across the manifold, but relative to somebody living on that manifold. So, when we're looking at our example with our ladder, where we're parallel transporting our ladder across the manifold of the curved surface of the Earth, because the ladder is remaining, constant relative to the person moving along with the ladder on the curved surface, we would say the covariant derivative, or the connection, of that ladder's movement. So the covariant derivative of a vector when we parallel transport it is 0. But obviously we might want to move a ladder or a vector such that it does change relative to somebody on the manifold. And so, there are cases where we'll be interested throughout this playlist on, non-zero covariant derivatives. And so it's worth spending a little bit of time trying to get to grips with what a covariant derivative is and how we would calculate it and relate it to our connection coefficients. So to start off with, if we're trying to intuitively understand the covariant derivative, or the connection as it's also known, we are going to look at how for example, how our ladder is changing as it's moved across the surface of the Earth, but we're going to be looking at that change from the perspective of viewing this ladder moving from space. Now, this isn't particularly useful computation in terms of general relativity, because this idea relies on being able to view the curvature of a manifold in a dimension that is one larger than the manifold. For example, if we're looking at the ladder moving on the surface of the Earth from deep space, we can see, the Earth is curved, but there we're talking about the curvature of a two-dimensional surface, but embedded in three-dimensional space. Whereas in general relativity, we don't want to talk about the curvature of space-time embedded in some structure with even more dimensions than space-time. We have no evidence that there are any other dimensions more than those of space-time. No firm evidence anyway. However, thinking about the covariant derivative extrinsically, so in a way that allows us to, for example, talk about components of the vector that is normal to the tangent plane, so is in the other dimension to the dimensions of our manifold, is useful visually, because we can imagine viewing how the direction of the ladder is changing from our perspective if we're looking at the ladder moving across the surface of the Earth, but from deep space. And usually when we think of curvature, we're thinking of two-dimensional surfaces embedded in three-dimensional space. So we're used to this kind of extrinsic notion of curvature. So if we wanted to calculate the covariant derivative of a vector, so how the vector changes across the hyperspatial axis, then what we could do is we could look at how the vector changes overall relative to the hyperspatial axis. And then if we wanted to see how the components on the manifold of our vector are changing, we just subtract how the vector is changing in the normal direction from the overall change. And this will just give us our covariant derivative, so how much the vector has changed relative to the manifold itself. Because if you're living on the manifold, the only aspects of the change of the vector you can deduce are the changes that lie tangent to the manifold, so lie along the manifold. And so you can do that by taking the total change in the vector in your extrinsic space, and then subtracting the part of that change of the vector that you can't see if you're on the manifold. So taking away the change in the vector that is normal to the tangent plane on the manifold. And it's worth saying, for a bit of notation, there are different ways to write the covariant derivative. Some people, for example, use capital D. I've used an upside down triangle. But because there are many directions we could consider the covariant derivative in, we can move our vector in lots of different directions, particularly in space-time, where our manifold is a four-dimensional structure. It's often helpful to indicate below the symbol for the covariant derivative something that is telling you in which direction we're taking the covariant derivative. And in terms of basis factors on the manifold itself, good basis factors are actually the partial derivatives. So you can read the left-hand side as the covariant derivative of our vector v along the spatial axis. That's how to read that left-hand side. An important thing to note is that if we're considering a vector that is moving across flat space, so imagine our manifold is flat and we move the vector across the manifold, well, if we're moving across the manifold, because the manifold isn't curved, the vector can just remain parallel to itself, even from an extrinsic perspective. That is, its normal component doesn't have to change. So for a flat space, the covariant derivative of a vector is exactly the same as the partial derivative of the vector. However, for curved space, the covariant derivative isn't the same, because if we have a curved manifold, there will be a change in the normal component to the vector that wouldn't be visible or doesn't exist in the tangent plane to the manifold. So that's kind of an introduction to the covariant derivative, but from an extrinsic perspective. And that's really good for getting a feeling for what the covariant derivative is and what it's describing. But now let's have a go at getting to an intrinsic understanding of the covariant derivative. So understanding how to calculate the covariant derivative if we don't have access to a dimension that is normal to the manifold. So we've now got a fairly intuitive extrinsic understanding of the covariant derivative. However, I haven't shown you how to calculate the change in the normal of a vector as we parallel transport it across a manifold. It's not directly obvious how to calculate that, and more to the point, as we mentioned, when we're dealing with, four-dimensional space-time, we don't want to make reference to, dimensions living outside of the dimensions on our manifold. Therefore, we want to get to an intrinsic understanding of the covariant derivative or the connection, and we ideally want to relate it to the metric. Now, how we're going to relate it to the metric is something I'll come on to in a little bit. At the moment, we're going to focus on an expression that will allow us to calculate it in terms of the connection coefficients. And that will be a good enough place to get to for now. So we're going to look at a quantitative description for the connection in terms of the connection coefficients. Now it's worth saying throughout this playlist I will try to avoid too much mathematical rigour, with the emphasis being on, instead doing the physics. The covariant derivative or connection and its relationship to the connection coefficients is one of those places where a lot of books and a lot of things get fairly abstract. So at the end of this derivation, our last step, I'm going to make a slightly hand-wavy argument. I hope you can forgive me. There are more rigorous material out there, but it's a kind of thing that I would encourage people who like a lot of rigour in the argument to look there at the end. But I want to keep this video as approachable as I can make general relativity. And it's subjective where to draw the line. what is regular to one person might not be to another. But anyway, let's get going with, I think, a fairly solid way of getting to the relationship between connection and the connection coefficients. So we're going to start with doing everything in terms of partial derivatives of a vector field. And remember, in flat space or in a manifold with no curvature, that's the same thing as finding the covariant derivative. But we're going to start with the partial derivatives of a vector field and then relate that to the connection coefficients. And when we begin, we'll see where the extrinsic nature or intuitive way to think about the covariant derivative comes out. So firstly, we're looking at finding the derivative of a vector field of V. And we're finding the derivative, or if you like, the gradient, in the mute direction. And look at this as general relativity. Convention has it that we use Greek indices, so Greek letters, for the indices of objects, mathematical objects, when dealing with general relativity. So I'm sticking to that convention. So, mu is just the, mute's coordinate. And we're using Greek symbols to, stay in line with general relativity. As an aside, when we're doing special relativity, you use Latin letters. I don't know whether going from Latin to Greek is meant to imply that we're going to something more advanced and abstract, but that, is the effect. The equations look more complicated, but, whether we're using Latin indices or Greek indices, they're acting the same way. They're still referring to coordinates. It's just Greek indices tend to refer to coordinates for space-time in the context of general relativity. Now we've already seen this. This is kind of the product rule for a vector field V, but written, using Greek indices rather than Latin ones. And if we want to bring in connection coefficients, which we want to do because we want to relate our partial derivatives to connection coefficients, so we can then later relate to the connection to connection coefficients, we recall the definition of the connection coefficients, and if we just substitute our expression into the gradient of our vector field or vector, well, we get this. Now, it's worth saying that from this equation we have at the bottom of our blue box, we see E gamma, and that is in fact indicating that the most natural way to think about the covariant derivatives involves some, taking into account, or the idea that there has been some change in a normal component to a vector as we move the vector across a curved manifold, but keep that vector as parallel to itself as possible, if you like. And so we have a different Greek indice for our term with our connection coefficient in it. So you can think of mu and u as the coordinates tangent to the manifold, and gamma is the coordinate perpendicular to the manifold. But if we want to think of the partial derivative and then the covariant derivative intrinsically, we don't want E gamma. We want everything to have a basis vector of E nu, so that we're working with basis vectors that are kind of tangent to the manifold, and ideally also the basis vectors we're expressing our vector on the manifold in. So we want new basis vectors to be specific. And we can do that in our last term by just switching our gammas to our u's and our u's to our gammas. And we can do that because although geometrically we're thinking of gamma as being, perpendicular to the tangent space, when we're doing computations, really we're summing nu's and gammas. We are going to be summing them due to Einstein's convention over all the dimensions we have available. So, if we were looking at a ladder on top of someone as they move across the surface of the Earth, we would be summing over, all three spatial dimensions. In general relativity, we'll be summing over all four dimensions of space-time, but we're summing over all of them, and therefore, providing we change nu to gamma and gamma to nu, we end up with effectively the same expression. Because we're adding the same terms together, we're just changing the sequence of the terms we're adding together. But it doesn't matter whether you do something like 4 add 2 add 4, whether you do 2 add 4 add 4, you end up with the same thing. So by switching around the Greek letters, we're just changing the sequence of the sum, which we haven't written, but by Einstein's convention of repeated indices above and below, we assume. So we're not changing the sum, we're just changing the order of terms in the sum, but we're free to do that. So to get to a more intrinsic definition, i.e. to get rid of our, basis vector in the gamma direction and replace it with a basis vector in the nu direction, we just interchange gamma and nu, and that leaves us with this expression where all I've done is in the final term on the right hand side, replaced gammas with nu's and nu's with gammas. And here we can at least on the right hand side factor out our basis vector in nu, leaving us with this. So this is saying that, the partial derivative of our vector field is now given by this, but, along the, direction that the vector was pointing. So this is a, change in the vector field, but, tangent to the vector at that point. So, tangent to the manifold. So we are getting closer to, well, we have essentially got now an intrinsic understanding of the partial derivative. But we want to get to the covariant derivative. Now, in flats, well, there's a couple of ways we could do it. We could argue it in a special case and then generalise it. So, in a special case, let's imagine our manifold is flat, so there's no curvature. In that case, we can pick a coordinate system where the basis vectors don't change across the manifold, in which case we could replace the partial derivative of a vector field with just the partial derivative of the components of the vector field multiplied by e mu, so the basis vector along which the vector field points. And that would then allow us to go, well, the partial derivative of the components of a vector field is equal to that thing we have in brackets, because we can factorise out our basis vectors. And then we could go, well, the covariant derivative just extends this idea to curved spacetime. We could also, however, think of it fairly geometrically. So the covariant derivative is looking at how a vector changes relative to somebody moving along with that vector on the manifold. So it's talking about how the vector would seem to change with respect to somebody on the manifold. And therefore, in that sense, the covariant derivative isn't really bothered by a natural change in the basis vectors across a manifold. And so we can just factorise out the basis vectors. And that last way of doing it is a bit more woolly, but it does emphasise that the covariant derivative is concerned with how a vector changes, but changes, you know, in ways that depart from how it would just naturally change as it moved across the manifold. And we end up with this final expression for the covariant derivative of the components of a vector field. Well, we have just cancelled out the basis vectors. Now, that last way of doing it is more woolly. As I said, there are more rigorous texts out there. I think formally a better way to think of it is just, consider the partial derivative in a flat space where you can pull out the basis vectors from the vector field. You can then cancel them out. Then you say the covariant derivative is just an extension of the partial derivative. So you replace the partial derivatives with our symbol for the covariant derivatives. And you can also say, well, yeah, okay, we picked to start off with a coordinate system where the basis vectors didn't change across flat space, but since the covariant derivative is a tensor, this is a tensor equation. If it works for a coordinate system where the basis vectors don't change across flat space, it will work for any coordinate system, including coordinate systems which have basis vectors that aren't changing on flat space. So, there's a few different ways to go about it. The main thing is our final expression, and to emphasise, this final expression is essentially describing how the vector would appear to change for somebody moving along with the vector on the manifold. So this covariant derivative really encapsulates an intrinsically changed vector, or how the vector intrinsically changes, and it's of this kind of change that we're interested in general relativity. Now you'll note this expression relates to the connection, or upside down triangle, to our connection coefficients. What we haven't done is related this to a metric. Now we don't need to relate it to a metric generally, but as we're doing general relativity, we really want everything fundamentally to come back to a metric. And you might wonder, well, how do we do that? Well, we recall that the connection coefficients, as you can see in the left-hand blue box on the screen, in the middle, the connection coefficients relate basis vectors to each other. The metric is about the inner product between basis vectors. So there should be a way to express the connection coefficients in terms of the metric, or the metric in terms of the connection coefficients. And that's where we're heading for the next bit of this video. So for the next bit, we're going to find essentially an equation where if you have the metric, you can calculate your connection coefficients from it. And in this case, the connection coefficients are called Christoffel symbols, or Christoffel symbols. I have to double check how to pronounce it, but it's one of those things. No physicists can usually agree on the pronunciation, but that's why we're physicists and not, linguists. So far in this video, we've got to a link between the connection and the connection coefficients. But we would like ideally to describe the connection, so how a vector changes as we move it across the manifold relative to somebody living on the manifold. We would like to relate the connection to the metric, and therefore we're going to want to relate our connection coefficients to the metric. So we want a formula in terms of our metric where we can calculate the connection coefficients. And so to do this, we're going to now insist that our connection coefficients have a couple of properties, and we'll explain what we mean, but we want them firstly to be torsion-free and secondly to be metric compatible. Now, if those phrases don't really mean much, don't worry. We're going to go over them, in detail now. So, firstly, the idea of them being torsion-free comes from the idea that, the partial derivative of a basis vector along, let's say, the first basis vector along the second axis should equal the partial derivative of the second basis vector along the first axis. And this is because since there isn't usually some preferential direction of space is fairly symmetric, there's no way to really distinguish x and y, we would expect the partial derivatives of a basis vector along the one direction to equal the basis vector of that direction's partial derivative along the first basis vector. You could also think of it in terms of scalar products, although it's not really formally defined in terms of that. It's related to the idea that the scalar product of vector A with vector B is the same thing as the scalar product of vector B with vector A. At least, if you're not doing, quantum mechanics, which we most certainly are not doing here. So all our vectors are real, and therefore our inner or scalar product, however you like to name it, is symmetric. A dotted with B is the same thing as B dotted with A. So there's lots of different ways to describe this, but essentially we're saying that, all dimensions of space are kind of equivalent to each other. And if we rephrase the statement we had in terms of relating our partial derivatives of our basis vectors, in terms of Christoffel symbols, we note the definition of the Christoffel symbols, and then just substituting the Christoffel symbols into our top equation. We can see that clearly, the statement that the partial derivatives are equal is equivalent to the statement that our connection coefficient is symmetric under exchange of the bottom two indices. So this kind of symmetry of our connection coefficients is based on the idea that we want a coordinate system describing a space where that space is kind of some degree of symmetry. So there's no torsion present in that space. The space isn't twisting. There's no preferred axis of space. When we come on to black holes that are rotating, so Kerr black holes, we'll relook over this idea of torsion-free in more detail, but there will be, really relating it more directly to the metric and talking about whether the metric is torsion-free rather than the connection coefficients. But you can, encode the statements of torsion or lack of torsion in the connection coefficients, if you will. And for a long time, we will not be worrying about spherical objects rotating in space or any rotation in space, and therefore we're free to just go, well, for the metrics we care about, we want our connection coefficients that we can get from the metric to be torsion-free, so to be symmetric under the bottom two indices. The next criterion that we want our connection coefficients to have is we want them to be metric compatible. Now, what does something being compatible with a metric mean? Well, it will mean that the metric can act on it as if that thing is a tensor. But we can reduce that rather complicated statement that the metric acts on something as if it's a tensor, in the case where that thing is the covariant derivative, by just saying that the covariant derivative of the metric is 0. And to show how this implies that the metric acts on the covariant derivative of a vector field as if the covariant derivative was a tensor, let's look at using this. Well, if we consider, acting the metric on the covariant derivative of the components of a vector field, because we've insisted that the covariant derivative of the metric is 0, essentially we could just put the metric, inside of our covariant derivative. It's almost like the reverse of the product rule, but where, the derivative of something, or in this case, the covariant derivative of something, that something being the metric, is 0. The metric is essentially not changing, it's acting as if it's constant in some way, and by constant I mean constant with regards to covariant differentiation. And using the fact that the components of our vector field are components of a tensor, we can contract that tensor, and we then can see clearly that the metric is contracting our covariant derivative. The also nice thing about this is we now can say that if we have the covariant derivative of a vector field, we can correspondingly get the covariant derivative of a one-form field. And since in general relativity, we might often want to use both vectors and one-forms in calculations, like finding the scalar product, this is a really, really useful condition. Being able to transfer between covariant derivatives of vectors and covariant derivatives of one-forms. But we call this metric compatibility because it's essentially saying the metric is acting on our covariant derivative as if the covariant derivative is tensor. And that ties up the metric with the covariant derivative. So, there are some justifications for using these two conditions, so something being torsion-free and something being metric compatible in itself, but the really good thing is using both of them together, we can come up with a unique equation that will allow us to find the connection coefficients if we have our metric. And by unique, I mean if we have a metric for a manifold, we will get only a single set of solutions for our connection coefficients. And the connection coefficients in this case are called Christoffel symbols. And in the next part of the video, to finish up, we'll be deriving that beautiful equation. So we've mentioned the condition of metric compatibility, but now we're going to use it to really get to some equations that link the covariant derivative of the metric, which remember is a tensorial-like thing, so it's independent of the coordinate system we pick. We're going to relate that to the partial derivatives of the components of the metric, which is dependent upon the coordinate system we are expressing our metric in terms of. And we're going to add a little bit on what the metric compatibility condition actually means. Now, if you're seeing general relativity for the first time, you probably thought, well, you haven't really seen the condition of metric compatibility before, but you have. You just might not have realised it. So when we were looking at special relativity, we looked at a metric where its components were constant. So at least in Cartesian coordinates, it had, constant components. So it would be natural to say, well, the derivative of the metric in special relativity, so the derivative of the Minkowski metric, a physically meaningful derivative, should equal 0. Because the metric isn't changing anywhere. All we're doing in general relativity is, having a slightly broader constraint upon our metric. So we're doing something similar, but we're not saying, well, the components have to be constant, even in a Cartesian coordinate system. We're saying the covariant derivative of our metric must be 0. And I've heard in certain, podcasts, even a, topologist who was doing a lecture, and, this topologist has spent many years looking at topology. Even he was unsure of how to visually interpret the condition of metric compatibility by itself. I'm hoping as we go through this playlist, we'll build together more clear intuition behind what this generalization of the idea of, the components of a metric being constant for flat space-time will build up a more general picture of what the generalization of that actually means, so how to visually interpret the condition of metric compatibility. But for our purposes right now, one thing it does that is really nice is it links the covariant derivative of a metric to the partial derivatives of the metric, and that's very useful because we can easily calculate the partial derivatives of a metric or the components of a metric. That's very standard. It's a lot harder at first to understand how those partial derivatives would have to relate to a much more physically meaningful covariant derivative. But our metric compatibility helps us get around this by linking partial and covariant derivatives together. And to see exactly how it does this, let's kind of recall a couple of key things. So firstly, the components of a metric in a coordinate system are given by taking the scalar or inner product between the basis vectors in that coordinate system. So obviously the equation here has to be true because by definition a component of a metric is the scalar product between the relevant basis vectors in a particular coordinate system. And these are kind of like basis vectors lying tangent on our manifold, at least around a particular point on our manifold. Now, using this, we can just bring both terms from our first equation in our kind of like cloudy box, if you like, to one side, and that's going to have to equal 0 because something minus itself is just nothing. But due to our condition of metric compatibility, we've set the covariant derivative of our metric to be 0. So now we can say, well, the partial derivative of a component of a metric minus the partial derivative of the scalar product between our basis vectors, our relevant basis vectors, has to equal the covariant derivative of a metric. And then some beautiful equations emerge if you just kind of expand the second term on our left-hand side, so the partial derivative of our scalar product of our basis vectors using the product rule, and then you make use of, our definition for the Christoffel symbols, because the Christoffel symbol is about how a basis vector changes. So it's very natural to use Christoffel symbols to help us expand the partial derivative of the scalar product between basis vectors. So once you've done that, once you've used the product rule, put in your Christoffel symbols in place of partial derivatives of the basis vectors, you'll end up with equations that look something like this. But we don't have to just kind of stop at this equation. We're free to change the letters if we will. And so there's a couple of other equations we can have which are simultaneously true due to our condition of metric compatibility. So we can also write our equation in this form, in form number 2, or in this form. And you might wonder, why have I got 3 of physically essentially the exact same equation? Why am I writing out the same equation in 3 different ways? It's because if we combine these 3 simultaneous equations with our condition of our connection coefficients being torsion free, then we'll end up for an expression that links our connection coefficients to the rate of change of our components of our metric. And playing around with that, we'll finally end up with our expression for our connection coefficients that can be derived solely from the components of the metric. And in that case, we can properly call our connection coefficients Christoffel symbols. In this video, I've been a bit lax. I've sometimes called them Christoffel symbols before this point. But really, it's only when you start bringing in torsion combined with metric compatibility where these abstract connection coefficients properly become Christoffel symbols. And the beautiful thing with Christoffel symbols is they will allow us to talk about the curvature of a manifold. And we can relate that curvature directly to the components of the metric, in line with the ends of relativity for kinetic time and space. So, it's quite really beautiful what we can do with our conditions of metric compatibility and torsion-free connection coefficients. And so to finish with this video, let's do this for the last part, where we'll get our final equation for our Christoffel symbols. So we've come so far and we've nearly got to the end of our adventure together for today. We've nearly got to a point where we can express our connection coefficients in terms of the components of a metric. But, we just have a little bit more to do to get there, and it's just using the conditions of metric compatibility and torsion-free connection coefficients, which we've kind of discussed during this video. So to get to our equation relating connection coefficients and the components of a metric, we start with metric compatibility. So in 1, I've just noted that since the covariant derivative of a metric is 0, we can just add covariant derivatives of metrics or subtract them and we'll still end up with 0. because essentially 0 minus 0 minus 0 is 0. You know, if you take away nothing from nothing, you end up with nothing. But as we saw on the last slide, there's a way to write number 1 but using our connection coefficients, and that's what I've done for number 2. So number 2 is just using what we saw on the last bit of the video, but using partial derivatives and connection coefficients instead of our covariant derivative symbols. Now you might look at this equation and think, God, you might look at number 2 and think, heaven, that's not good heaven, but like, oh my God, has the wrath of God descended upon the world? Because it is a long equation. And this is one of the reasons why one doesn't look at non-Euclidean geometry in high school, because it would absolutely terrify students in high school and probably never want to see any geometry ever again. But thankfully, in addition to metric compatibility, we have another condition we can use to drastically, and I mean drastically, simplify equation 2. And that's the condition of torsion-free connection coefficients. So if we use the idea that the connection coefficients are torsion-free or are symmetric under the bottom 2 indices, and we also use the idea that, our metric is diagonalized, if we express our metric as a matrix, and so our metric is symmetric, then we can simplify 2 drastically, and we end up with a single, still abstract and complicated looking, but definitely a lot nicer than number 2 looking equation. So our equation in blue relates the components of the metric to the connection coefficients, and when we calculate the connection coefficients in this way, we say we are finding the Christoffel symbols. So the Christoffel symbols are a version, a special case if you like, of the more abstract idea of a connection coefficient, but where it's related to a metric which is, where the covariant derivative has metric compatibility. Now you might wonder, I've outlined the steps to get to the blue equation. I haven't gone through every single step in a huge amount of detail, because then these videos will become really, really messy and will disguise the key principles at play. But given I haven't gone through, all the steps in a huge amount of detail, you might wonder, well, is there another way to calculate a connection coefficient from a metric which has metric compatibility with the covariant derivative, and where the connection coefficients are torsion-free? And it turns out this is not the case. It turns out the equation we have in blue is unique. It's the only equation that will relate connection coefficients to the metric in a way that ensures the covariant derivative is metric compatible and the connection coefficients are torsion-free. And for those of you who, might be doing some background reading in general relativity in other areas, it's worth mentioning this relationship between connection coefficients and the metric is called a Levi-Civita connection, not to be confused with the Levi-Civita symbol or tensorial-like object. Now, through this video, I've sometimes, instead of saying connection coefficients, said Christoffel symbols, You might wonder, where does that come from? Well, you know, did I say that right? I think I did. I may say throughout this video I've used Christoffel symbols instead of connection coefficients. Hopefully I said that the right way round. But the reason why sometimes we use the word Christoffel symbol is because when our connection coefficients are expressed in terms of our metric, as we have in the blue equation, we say our connection coefficients are Christoffel symbols. So in the case where you express connection coefficients in terms of the metric, the connection coefficients are just called Christoffel symbols. And the fundamental theorem of Riemannian geometry says we have found a unique equation for these Christoffel symbols. With Riemannian geometry essentially being geometry about a manifold or objects that live on that manifold, so for our purposes, the geometry of space-time, or four vectors that live on space-time, in terms of a metric. In Riemannian geometry, the focus is the metric, and all other properties, for example curvature, which in the next video we'll discuss more of using our Christoffel symbols, ultimately can be calculated from the metric. If you know the metric, you in principle know everything about the manifold, or in our case the space-time you're dealing with. So that's kind of everything for this video. We've come a long way, and particularly if you've got to the end of this video, thank you very much for staying with me through all the Greek letters and through the mammoth equation, which is equation 2. In terms of plans for the rest of this month on the playlist, I probably won't be posting any big conceptual videos on the general relativity playlist, at least for just kind of the rest of this month. However, I am hoping to do a couple of 10 to 15 minute videos where I use some of the equations we have looked at, but in specific cases, so you can see how the maths works. Like, I might have a go at, calculating the Christoffel symbols for, flat space described in plane polar coordinates, or something like that. So you can see specific examples of the maths. Whereas I try to keep the big concepts to these kind of longer videos where there's more time to kind of talk and the focus is less computational and more, here's the maths we're going to use to describe these ideas, and here is how these ideas or the maths kind of all relate. So, I hope you have a good rest of this month. If I don't see you, on this playlist for a week or so, at least probably. But I am looking forward to doing some more general relativity videos. Hopefully soon. I've got some good ones planned. And maybe even my cat Ara might join me for some of those, and I can, share her wisdom on general relativity. But anyway, I hope you had, a good time with these videos, learned something from it, and I'm wishing you a wonderful week ahead. But everything for now, and I'm looking forward to sharing with you some more wonderful physics soon.